Welcome everyone. In this video we are going to be solving the entire paper of physics paper 2 O level October November 2021. Alright, so as you must already know, paper 2 is supposed to be 1 hour 45 minutes long. It has two sections. Section A you have to do all the questions, and in section B you have to do 2 out of 3 questions. The total marks for this paper is 75. Alright, let's get moving. Question number 1. You have some liquid in the jug. You have been given an electronic balance. You have been given a measuring cylinder, and they're saying, well, the electronic balance uses the weight of the measuring cylinder to determine its mass. The weight and mass have different units, so they are telling you a difference between the weight and the mass. They're saying, well, state two other differences, two other ways in which weight differs from mass. So one of the ways is that weight is a vector, whereas that mass is a scalar. Now you must remember what is the difference between a vector and a scalar. A vector has direction, whereas scalar has only magnitude but no direction. Vector is a force, mass is not a force. Another important difference apart from units and being scalar and vector is that weight changes. Weight changes and mass always remains the same. Now weight changes. When does it change? Let's suppose you are on Earth. The gravitational field strength, which is G on Earth, is approximately 10. But if you go to the moon, let's suppose, the gravitational field strength there is about 6 times less. So your weight will also be 6 times less. So weight changes with the gravitational field strength. If the gravity is weak in a certain part of the universe, the weight is also going to be smaller, but the mass will always remain the same. So weight changes with gravitational field strength. Pretty straightforward question. Another easy question. So you are asked to determine the density of the liquid using the apparatus shown on figure 7.1. By the way, in your syllabus, not only you're supposed to know how to find the density of a liquid, but you should also know how to find the density of regular solids and irregular solids. So for this particular experiment, you must know that you need mass and volume to calculate the density, since density is mass over volume. Where's the volume going to come from? This is where the volume is going to come from. The mass is going to be given by the electronic balance. But the problem with electronic balance is that if you place the measuring cylinder on it and then you add liquid to it, it will measure the total mass of the cylinder plus the liquid. We only need the mass of the liquid, so you have to subtract the empty measuring cylinder's mass. So okay, so now we have, using these steps, we have found out the mass of the liquid. Now the liquid is already in the measuring cylinder, so you just need to read the volume from the measuring cylinder. So now you have the mass as well as the volume. You'll say calculate the density using mass over volume. And that's pretty much it. Alright, now we have been given the density of the liquid and we have been given the mass of the liquid. The density is in kg per meter cube and the mass is in kg, and we can now calculate the volume in meter cube, which is what we are required to do. So the formula for density is mass over volume. Obviously then volume would be mass over density. So if we calculate that, that would be 0.65 over 780, and that should give us around 8.3333 times 10 to the power minus 4 meter cube. Make sure you are combining the units properly and you're not messing them up. So I'm just going to round it off to two significant figures when I write down my answer, and Do not forget the unit. All right. Moving on to question number 2. So they're saying force is a vector quantity. State what is meant by a vector. Now remember, whenever they write this command word, what is meant by, all they're asking you is the definition of the term. They're just asking you the definition of the term. So it is a physical quantity. It is a physical quantity with both magnitude. By magnitude we just mean the size of the quantity. So for example, when I write 24 Newton, this 24 right here is the magnitude of the force. Magnitude and direction. What is another type of physical quantity? Well, another type of physical quantity is a scalar and it has no direction. So make sure you know what are scalars and vectors and what are some examples of scalars and vectors. All right. Moving on to part B, you are shown a swimmer who is pushing against the end of the wall in order to propel himself. Let's call this force that he's exerting on the wall F1. Now, when he pushes against the wall, he accelerates away from the wall. And they're saying, explain why it happens. Why is he accelerating away from the wall? And they've also asked you to explain it using Newton's third law. Well, when he pushes on the wall, according to Newton's third law, he will also experience an equal and opposite force, F2. Now this F1 and F2 are actually equal to each other and they're opposite in direction. So first of all, we're going to say so he exerts a force on the wall and the wall exerts the equal and opposite force on him. Now, why is he accelerating? Well, there's a simple relationship between force and acceleration. If anything is experiencing a resultant force, then you can find out its acceleration with this formula. So since there is a resultant force acting on the swimmer from the wall, he is going to accelerate in the same direction. Since there is a resultant force on him, away from the wall, so he accelerates in the same direction. It's very important to note that the direction of the acceleration will be the same as the direction of the resultant force, which is away from the wall in this case. Now they're saying that there is a constant forward force on the swimmer. So let's make the swimmer here. There is a constant forward force on the swimmer. Let's call that force F. Now they're saying his speed increases and eventually reaches a constant speed. Well, why doesn't he accelerate forever? Why is his speed becoming constant after a certain amount of time? And that is what we need to explain here. And this is again a 3-mark question. So what you need to explain here is that this forward force is not the only force acting on the swimmer. Actually, he is also going to experience a backward force, which we call the drag force. So let's just first mention this. So there's not just one force acting on him. There's 2 forces acting on him and both of them are in the opposite direction. Now the thing with this drag force is that it depends on speed. This increases with speed. So if a speed is increasing, the drag force will also keep getting bigger and bigger. On the other hand, the forward force remains constant. So we say the drag force increases as speed increases. So now we know that the drag force becomes weaker and weaker, bigger and bigger. So you will find out the resultant of these 2 forces by subtracting them. So of course, if the drag becomes bigger and bigger, the resultant is going to get smaller and smaller, and eventually the drag will be equal to the forward force. Eventually drag will be equal to forward force. So the resultant is 0, and if the resultant is 0 as explained above, if this resultant is 0, then acceleration is also 0. So question number 2 is also done. Let's move on to question number 3, and this question is from the chapter of light, specifically from the topic of refraction and total internal reflection. So light is passing from air to a transparent block, and you've been given certain angles, and they're saying light travels more slowly in the block than air. Explain how the figure shows this. How can we know that the light is fast here and the light is slow here? How do we know that? Well, you have to remember, whenever the light is bending towards the normal being this dotted line, whenever the light bends towards the normal, it will always slow down. If whenever the light bends away from the normal, that's when the light is speeding up. So first of all, we're going to mention, this is a 2-mark question, so we need to write 2 points. The first point is that now this means that if I, let's say, name this angle the angle of incidence, and I name this angle the angle of refraction, then I know that the angle of incidence is greater than the angle of refraction at the moment, right? Angle of incidence is greater than the angle of refraction. Now the refractive index, which we also represent with the letter n, is the ratio of speeds, right? It is the ratio of speeds. In fact, the formula for it is c over v, c being the speed in air and v being the speed in your medium, which is the transparent block in this case. Now this refractive index is also given by the formula sine I upon sine r. Now think about this. If sine I upon sine r is also equals to the refractive index, which also has the formula c upon v, then these two fractions are equal to each other. Now c is the speed in air and v is the speed in your medium. You can see from the diagram clearly that angle I is the bigger one. So if angle I is larger than the denominator, then it must be true that the speed c must also be larger than speed v. And this is how basically we are proving that by looking at the diagram, by mentioning that the light bends towards the normal, it is slowing down, and whenever it bends away from the normal, angle r will be larger and therefore v would be larger. Alright, moving on to part 2, which says describe what happens or state what happens to wavelength and frequency. First of all, you should remember one thing: frequency depends on the source. Alright, now you're not changing anything about the source. You can't change. In this question, there is no mention of changing anything about where the light is coming from. So if the source has not changed, the answer for frequency, which is mostly, is that it remains the same. Frequency will not change. That is the answer. Now go back to your wave equation, which is a very common equation in this chapter. Speed is equals to wavelength times frequency. Now you have already mentioned that speed decreases, and you're saying nothing happens to frequency. Then you can clearly see that the wavelength and speed are proportional. So if speed is decreasing, if the light is slowing down, then wavelength is also going to decrease as the light enters the glass block. So remember this: whenever the wave, not just light, any wave slows down, the wavelength will decrease, and whenever it speeds up, the wavelength will increase. Whereas if you're doing nothing to the source, which is mostly the case, frequency will not change. Alright, now you're being given the refractive index of this material as 1.6 and the angle theta is given as 45, and you have to find the angle phi. Let's go back to our diagram and take a look at these angles. I'm just going to remove my old names. And what they're saying here is that this angle on the outside, the angle of incidence, basically, which they are named theta, is given as 45. And you have to find this angle. However, you can't find this angle directly because from the formula, from the method that we have studied, you can first find this angle R. You first have to find this angle R, which is the angle of refraction. And the formula to do that is refractive index equals sine I over sine R. Now in this case, the angle of incidence is written as theta. So this is what I'm going to write here. Since refractive index is 1.6, sine theta will be sine 45 and sine R is unknown. So I'm going to write sine R as the subject, and then we're going to calculate the right hand side. So that gives me sine 45 over 1.6, and that gives us sine R equals 0.4419. Now many students which are a bit weak in maths forget the next step, and they basically just leave it as the answer, and that is not the case, because in order to find R, what you need to do is you need to take the sine inverse of your previous answer. So we need to do this. So you press shift sign on your calculator, you get sine inverse, and in the brackets you put your answer, and you will get your angle R, which is 26.227 degrees. However, this is not the final answer, since we wanted to find angle theta. And you can clearly see that if this entire angle is 90, then 90 minus R should give you angle phi. So angle phi would be 90 minus 26.227. And that should give us our final answer, which is 63.77. So I'm just going to round it off to 63.8 degrees. All right. The next question says that the angle of incidence angle I at the bottom is equal to theta, equal to phi. So going back to our diagram, it says that this angle right here is the same as this angle, which means that if angle phi was 63.8, then angle I is also 63.8. And now it's mentioned that the critical angle for this material is 39. So what happens to light? Well, let me remind you what happens to light. Let's take three situations. This is the boundary between two mediums, and the light is arriving at different angles at these boundaries. So let's suppose the angle of incidence here is 30. Remember, the critical angle for the material is 39. So right now you can see that the angle of incidence is less than the critical angle. In the second case, let's suppose the angle of incidence is 39. So what we're saying is the angle of incidence is equal to the critical angle. And in third case, the angle of incidence is 63.8, which is what we need to explain what happens here. In this case, the angle of incidence is clearly greater than the critical angle. So what happens to light? If the angle of incidence is critical and less than the critical angle, then the light will simply just bend away from the normal as it is going from the transparent block into air, so it speeds up and it bends away from the normal. This is refraction taking place, and there's a bit of weak reflection here. Some of the light also reflects back, but most of it refracts. If, however, the angle of incidence becomes large enough that it's equal to the critical angle, then the light refracts such that its angle of refraction becomes 90 degrees. So angle of refraction becomes 90 degrees, and the light travels along the boundary. Some of it will also reflect back into the medium. However, if the angle of incidence becomes greater than the critical angle, then the light is not going to go into the other medium. In fact, all of the light is just going to reflect, and this is what we call total internal reflection. So when they ask what happens to light, you see that the angle of incidence, which is this, is greater than the critical angle. So you say the light will undergo total internal reflection. Now, the command word says explain. So you just don't have to describe, you just don't have to state, but it asks you to explain, and the question is 2 marks. So the second mark is for the explanation, and the explanation is that the angle of incidence is greater than the critical angle. And that's it. All right. All right, continuing with question number 4. We have a washing machine which is working normally. Now, this is an important point to note. When it's working normally, both the heater and the motor are switched on, and it's connected to a main supply by a cable. In the live wire, the current is 13 ampere. What's the current in the neutral wire, and what is the current in the earth wire? Well, let's suppose this is your washing machine, right? What happens is, here is your motor and heater, the internal components. The live wire will get connected, and also the neutral wire will get connected to the motor, and both of these are obviously connected to an AC supply. On the other hand, the earth wire will be connected to the metal body, and it will be grounded. Now, when the machine is working normally, then where is the current supposed to go? The current is simply supposed to go to the motor and the heater from the live wire, and it's going to go back through the neutral wire. The earth wire is not being used at the moment because it is only connected to the metal body. It's not connected to the working components, and the earth wire is only in use briefly when and if there is a live wire touching the metal casing, and let's suppose the metal casing is also exposed to the wires, but that is not the case. So in the neutral wire, the current is going to be 13 amperes, whereas in the earth wire, the current is simply going to be 0 amperes. And I hope that's clear. Now they're saying the insulation in the mains cable is now damaged and the washing machine vibrates. The live wire touches the metal casing. So here's what's happening now. Your live wire is now exposed to the metal casing, and this is gonna be a problem. And why is that the problem? Let's just first show a damage here. So this is where the damage has happened, and the live wire is now touching the metal casing. So the entire metal casing is also now live. In this case, if the user touches the metal casing, he will get electrocuted, and that could obviously be a dangerous situation. But they're saying the earth wire and the fuse work together to prevent damage. So how do they prevent damage? How do they basically just stop this process of damage to the person as well as to the washing machine? Well, what happens is that the earth wire is a very low resistance wire, right? So first mention the earth wire is a low resistance wire. The ground. So now how does the current travel in this particular situation? Now what happens is that the current will travel from the neutral wire to the metal casing and through the earth wire into the ground. And since the earth wire is a low resistance wire, this current will be brief and large. The current will now be large. All right. Now in your live wire, what you have is a fuse connected. This is a fuse. And the job of this fuse is to make sure that the current does not exceed the rated value, which is 13 ampere in this case. So if the current is now greater, more than 13 amperes, what happens to this fuse? The fuse blows up, it melts, and it disconnects the circuit. this is how further damage is prevented. When your machine is going to stop working, you're going to call a technician and he's going to look at the machine and he's going to figure out the fault. So the machine will not be damaged any further. So you can't replace the fuse straight away. The fuse has to be replaced after the machine's fault has been fixed. Now they're saying, why is the live wire the location where the fuse is connected? Why is the fuse connected into the live wire, and why not the neutral wire? Because a current can also flow through the neutral wire. Well, the thing is, if the fuse was connected into the neutral wire, and let's suppose that was the case, so let me just hypothetically give you a situation where the fuse is connected into the neutral wire. So let's draw the fuse here. Now what is the path of the current? The current has to flow, the large current has to flow from the live wire to the metal casing and then through the earth wire into the ground, right? The fuse here is basically useless. The fuse is not being used at all because there is no current passing in the neutral wire through the metal casing, and therefore if someone touches the metal casing of the washing machine, they might still get electrocuted because the fuse is not doing its job. It's not melting, it's not disconnecting the circuit. So what we'll say is the live wire is the one out of the neutral wire, and the live wire is the one which is at high voltage. Alright, moving on to question number 8. Now this question has two parts. Either you'll do this page or you can do this page, but obviously we are going to cover both in our practice at the moment. So the question says that you have a DC power supply and an LDR, light dependent resistor, and you have 2 ammeters. The reading on the ammeter 1 is 1.6 amperes. So make sure that you know that the current passing from here is 1.6 milliamperes. Calculate the time taken for 7.2 coulombs of charge to pass through ammeter 1. So the relationship that you will use here is that current is charge over time. So if you rearrange, time will be charge over current. So you have a charge of 7.2 coulombs and you have a current of 1.6 milliamperes. So you convert that into amperes, which will be 1.6 times 10 to the power minus 3 amperes. So when you do that, you will get your time, which will be, let's calculate this, 4500 seconds. Sometime later, the brightness of the LDR decreases. What happens to the reading on ammeter 2? Alright, so the brightness of LDR decreases. What happens when the brightness of LDR decreases is that its resistance increases. Now they're asking what happens to the reading here. The thing is that across this branch, the potential difference is still the same because that depends on this power supply. So potential difference across N remains the same, and resistance of N is also the same. Now ammeter reading is the current, which is V over R. If V has not changed and R has not changed for a resistor N, then obviously the current passing through here will also not change. So the reading does not change. Now they're asking what happens to the time taken for this amount of charge to pass through ammeter 1. Now remember, in your previous part, you use this equation, time is equals to charge over current. Now obviously the charge that has to pass is still the same. They still want 7.2 coulombs of charge to pass through ammeter 1. However, what happens to current? If you are able to decide what happens to current, you can also explain what happens to the time using this relationship. So let's look at what happens to this total current, which was previously 1.6 amperes. What happens here? Since the resistance of LDR has increased, brightness decreased, so the resistance of LDR increased, the resistance of this entire branch and obviously the entire circuit, the entire combinations resistance is gonna be increasing now. So if resistance increases, what happens to the total current? Obviously the current is going to decrease. So we're gonna say total resistance increases. So current decreases. Now, if current is decreasing, you can clearly see that time is inversely proportional to current here in this relationship. So time will increase. Moving on to the other part of this question, which is the other option that you have. Either you will attempt this page or the previous one. Now you've been shown a component and you're asked to write the name of this component, and this is a transistor. Remember, this is the question from the topic of electronic systems, which is an optional chapter in paper 2. So now this transistor is being fitted into a circuit which also has a relay and a motor and an LDR in it. So you are being asked what happens to LDR if the brightness increases. Well, first of all, we're gonna say the resistance of the LDR is going to change, and it's a reverse relationship. If the brightness increases, the resistance of the LDR decreases. And they're asking, explain why the motor switches on. So you can clearly see that the motor is totally not connected to this power supply. It doesn't have anything to do with the LDR. So then how does it switch on? Well, that's because the two circuits here are connected or are joined together via a relay, which is not an electrical connection. A relay basically is a switch which uses a small current to switch on a large current. So we're going to say how the transistor and the relay work together to switch on the motor. In fact, the LDR, the relay, and the transistor, all three work together to switch on the motor. Now what happens is, when the resistance of LDR decreases, there will be a current flowing here. Now remember, this side of the transistor is called the base, this side is called the emitter, and this side is called the collector. Whenever a small current starts to flow into the base, that's when the transistor switches on, and that's when the current can also flow from collector to emitter. If there is no current here, then no current can flow in this direction as well. So right now, since the resistance of LDR decreases, there is a current that will flow into the base of the transistor. And now you can see that the current can also flow from collector to emitter, so the current is flowing through the relay as well. So a current can flow through the relay coil. Now this rectangular part of the relay is known as the coil. When the current passes through it, the coil is magnetized. So we'll say the coil is magnetized, which basically attracts this switch, and the switch closes. Magnetized, and the switch is closed. So now what happens is, if this switch closes, you have this circuit which is complete. Therefore, a current can flow through the motor and the motor will get powered from this mains supply. It is important to note that no current flows from the cell to the motor. The cell is not powerful enough to run the motor. The motor is probably connected to a 220 volts mains supply. This switch just closes and now this path is complete. A current will flow like this in the motor. Alright. So the coil magnetizes and the switch is closed. So the motor is now connected to the mains supply. Alright. To question number 6. This one is from nuclear physics and radioactivity. So we have a radioactive isotope X and it decays by alpha emission and becomes a stable isotope. They're saying what changes happen when it emits an alpha particle. Well, you must know that an alpha particle consists of 2 protons and 2 neutrons. So that's the change that occurs in the nucleus. It loses 2 protons and 2 neutrons. So now they're saying there's a detector in the laboratory, but there is no samples around. However, when the detector is switched on, it shows you the count rate of 22. Now, why is that the case? Well, what is it detecting at the moment? It is not showing you 0 reading, but a number other than 0 because there is always a certain amount of radiation present around you, and we call that the background radiation. So we're going to say it is measuring the background radiation. Therefore, in your detector, you will never get a 0 reading. Okay, now the sample X is placed 2 centimeter from the detector and the reading now rises to 8000. So definitely the alpha particles from the sample are being detected by the detector. However, when it's moved a distance 10 centimeter away from the source, the count rate reduces to the background reading again. Now it drops back to the original value because it's not detecting any radiation at all now from the source. So why is the radiation not being detected by the detector? Because the type of radiation emitted by the source is alpha, and alpha particles cannot travel more than a few centimeters in air. They'll just travel around 4 to 5 centimeters and that's it. So you're gonna say so the reading drops back to background radiation. Alright, now you're being shown an alpha particle which enters a magnetic field, and right now this magnetic field direction is not mentioned to us, and they're asking you at point J to show the direction of the force on the alpha particle. Now remember that alpha particle is positively charged, so the flow of alpha particles is also the same as conventional current. And if you are being told the direction of the magnetic field, you can actually find the direction of the force using the Fleming's left hand rule, just like you find out the direction of the force on a current carrying wire passing in a magnetic field. However, in this question, you can clearly see that the alpha particles are deflecting upwards, so the force on them is upwards. But here is the thing about magnetic fields. When the alpha particle is here, the force will definitely be upwards. But as the alpha particle keeps changing direction, the force also keeps changing direction. And the thing about alpha particle, the magnetic fields, is that they always exert a force at 90-degree to the path of the particle. So when the particle is around here, the force might be something like this. When it's here, the force will be somewhat like this. And for our answer, try to draw an arrow which is at 90 degrees to the path of the particle. So this is what happens to the force. It always stays at 90 degrees to the path of the particle. So this is how we will draw the arrow of the force. Always 90 degrees to the path. Now they're saying determine the direction of the magnetic field and indicate the direction. Alright. Now here, as I was just explaining, you can find out the direction of the magnetic field using the left hand rule. And why is that? Because you know the direction of the force, you know the direction of the current. The only thing that you do not know is the direction of the magnetic field. And once you apply this magnetic field, this Fleming's left hand rule to this particular diagram, your current will be the direction of alpha particles. So your middle finger is going to be pointing in this direction. The force on the particle is upwards, so your thumb should be pointing upwards. And automatically you will find that when you do this, you find out that the direction of the magnetic field or the direction of your index finger is pointing into the page. Therefore, the answer will be into the page. The direction of the magnetic field is into the page. Now they're saying explain whether the force does work on the alpha particle. Now you must remember that work done is force times distance, but this distance is distance traveled in the direction of the force. Let me give you an easier example first so we can come back to the question above. If you have a box here which is placed on the ground and two people decide to exert force on the block in order to move it to its new position, which is here. So this is the distance covered by the box. Now one person decides to exert a force F1 like this, and the other person decides to exert a force F2 like this. Which force is doing the work on the block? Only force F1 is doing the work on the block because the distance that is traveled is in the direction of the force. F2 is not doing any work because the distance traveled is not in the direction of the force. Now in our case, you could see that wherever the position of the alpha particle was, the force was always 90 degrees to it. If this is the velocity of the alpha particle, the force is at 90 degrees. If the alpha particle is somewhere here and its velocity is like this, then the force is at 90 degrees to that. If at point J the velocity is somewhat like this, then the force is 90 degrees to that. So since the force is always perpendicular to the motion, we say that no work is done. No work is done at any given point. We're gonna start section B. Remember that in this section there are total 3 questions, but you are only required to do 2 of them. However, for this paper we are going to practice all of them, and this question here gets quite complex in the later parts, so be very careful with this and pay attention. So what we have here is a hydraulic system, or what you can call a hydraulic press. This is part of the chapter pressure, and it also includes some of the concepts from the chapter of work, energy and power. So what happens is that you exert a force from here as an input, but the thing about this hydraulic press is that it gives you mechanical advantage, and it exerts a much larger force here on the waste, and then it's able to compress the waste so that it can be then, thrown into the landfill sites. So this is basically a recycling center, and what they're doing is they're trying to compress the waste material, so they need a large force. Now even though the force here is very small, still a large force is being exerted on the waste. So how does that happen? This is what the question is about. Now when force 1 is exerted on piston 1, the oil is pushed along the pipe and the piston 2 moves downwards, and piston 2 compresses the waste. Oil is a liquid. State the property of the liquid that makes it suitable for use in a hydraulic system. So the thing with liquids is that we want all of the pressure to be transmitted along the liquid, and for that the liquid must be incompressible, and that's what most liquids are. They are incompressible. No matter how hard you apply pressure on them, you cannot reduce their volume, unlike gases, where if you uh, put pressure on the gases, the gases are going to compress and they are going to reduce in volume. So liquids are incompressible, so they transmit basically all the pressure that you exert on them. Now, in terms of molecule, why the liquid is incompressible is what they're asking. So the thing with liquids is that their molecules are quite close together. Their molecules are very close, and if you try to push them together any closer, the thing about the force between the molecules is that it turns repulsive. We have all studied that the force between the molecules is attractive, which is holding them together. But if they come too close, then that force turns repulsive. So there will be a large repulsive force if we push them together. Now, what is the advantage of using oil? You could have also used water or any other liquid, but why oil? Well, there is an additional advantage as well. Think about these pistons, and they are rubbing across these surfaces here as well and here as well. The thing with oil is that it's a very good lubricant. So what it does is that it reduces friction. Oil will reduce friction because it's a good lubricant. Always remember that questions that start with suggest will have more than one answer to them, and you can just use your common sense most of the time and your prior knowledge to answer these. Now, the cross-sectional area of piston 1 is 0.018 meter square, and the force exerted on it is this. So we want to find out the pressure. This is relatively straightforward because pressure is force over area. So that would be 4500 over 0.018, and when you calculate that, we'll get around 250000 pascals. Now this is a large number, so I would like to write it as standard form, although even if you don't, it's not a problem, but do not forget the unit. Either write pascals or you can write Newton per meter square. Now the atmospheric pressure is this. So what is the total pressure in the pipe? Now, due to this force, the pressure was 2.5 times 10 to the power 5, but due to the air around it, it is also exposed to atmospheric pressure. Anything that is exposed to the atmosphere around it will have atmospheric pressure acting on it as well. Therefore, the total pressure will be the pressure that we calculated in the previous part plus the atmospheric pressure. So that will be 1.0 times 10 to the power 5 plus 2.5 times 10 to the power 5, and that gives us 3.5 times 10 to the power 5 pascals. Now the piston 2 that is in contact with oil is 1.4 centimeter square in its area. Initially the upper surface is at level with point P. So what they're saying is that the piston is initially at this point. Alright. Calculate the force exerted on piston 2 due to the pressure calculated in C part 2. So the thing with these hydraulic presses is that all the pressure gets transmitted through the liquid, and the same pressure is exerted on the other piston as well. And remember, it's the pressure which will remain the same. So if the pressure P1 on piston 1 was 3.5 times 10 to the power 5, then pressure P2 will also be 3.5 times 10 to the power 5. Now we want to find the force. So this P2 will obviously force 2, the force on piston 2, over area A2 of the second piston. We already know the pressure. We can also write this formula as F1 over A1, but we have already calculated the total pressure on piston 1, and we can write that here directly, 3 times 5 times 10 to the power 5. Now this area is given to us, which is 1.4. So you can see that the pressure remains the same on the other piston, but since area increases and since area is being multiplied by the pressure, the force becomes very large. So the force on the other piston is now going to be much larger than the force that was on piston 1, and it's basically 4.9 times 10 to the power 5 Newton. Now compare that to the force on the previous piston, which was only 4500 Newton. This is much larger than that, almost, I guess this is almost more than 100 times larger than the other force. So the bigger the area, the bigger the force on the other piston. Now, as piston 1 moves along the pipe, what happens is that the pressure of the oil in point P remains constant. Piston 2 moves down and the pressure of the oil on piston 2 increases. So they're saying pressure throughout the liquid is the same. But since this piston is now moving down and it's below point P, so there is more pressure being exerted on this piston. But just think about why that is the case, because that's what the next question is asking you. Why the pressure on piston 2 increases? So you have to pay attention to the diagram and think about what does the pressure in a liquid depend on. This was the initial position of the piston and now it's down here. So what you have is a bunch of liquid above the piston and the depth has now increased. The depth of the liquid has now increased. This depth H that I have marked here will cause a pressure on the piston 2 additionally. And if you must remember, the pressure of a liquid actually is calculated by this formula, rho GH. So if this increases, then pressure is also going to increase. So you're going to say the hydrostatic pressure, which is the pressure exerted by the liquid. You can also say the pressure due to the liquid increases because the depth of the liquid column above it increases. And now they're saying that the density of the oil is this, and the piston 2 has moved this amount of height. This is the height that has changed. This is the density. And they're saying calculate the increase in the force on the piston 2. But you can't find this out directly. You also have the G here. You first of all will have to find out the increase in pressure. You will have to find out the increase in pressure. So that will be calculated by rho GH. Now the density of the oil is 900. G is obviously 10, but the change in height, which is marked here on the diagram, by the way, I've marked the height here. This is the change in height, that is 0.5. So the greater the change in height, the greater the pressure. So now when you calculate this change in pressure, you will get you'll get around 4500 pascals. Now you have the change in pressure, so it's quite easy to calculate the change in force now, because force is pressure times area. So 4500 times the area of piston 2, which was 1.4, you will get 6300 Newton. Last part of this question. Air is trapped in plastic bags that contain the waste. The temperature remains constant. Explain in terms of molecules why the pressure increases. So here's the thing. We have studied that if temperature remains constant, then pressure is inversely proportional to volume. So if volume decreases, pressure increases. But we are being asked to explain it in terms of molecules. So the thing is that these molecules are always moving around and hitting the walls, and these collisions with the walls cause the pressure. If these collisions are more and harder, then the pressure will increase, and if these are less collisions, then obviously the pressure will decrease. Now when bags are compressed, the volume decreases. So there is less space for the particles, and what's going to happen then? They will collide more often. So make sure you do not write that the frequencies and the collisions are harder, or they collide faster, or they collide at a greater with the greater force on the wall, because the temperature has remained constant. So the force of the collision is still the same, but there are more number of collisions in a given amount of time. So since the frequency of the collision increases, the pressure also increases. So that's it for question number 7, and now we're only left with 8 and 9. All right, so now we will move on to question number 8, and this question mostly deals with the chapter turning effects or moments. Now you have been shown an irregular object, and a force is acting at point P as shown by the arrow, and X is the point which needs to be treated as the pivot. So they're saying, first of all, write down an expression that defines the moment. Write down an expression for the moment. So we know that moment is F multiplied by distance, which is D. But you have to draw on the diagram to show what you mean by the distance. So what would be the distance? Would it be this? That is totally wrong. This is not going to be the distance. In fact, you have to be able to explain that this distance is the perpendicular distance from the pivot to the line of action of the force. So from point X, if I want to draw a perpendicular line to the line of action of force F, then that should make a 90-degree angle with this line. So this is how I will represent distance D. Alright, state the principle of moments. So principle of moments applies to objects that are in equilibrium, objects that are balanced. And the thing with those objects is that if they are balanced, then the clockwise moments and the anti-clockwise moments are equal to each other. So the principle of moments is moving on to the second part. It is saying describe an experiment to verify the principle of moments. Include a diagram as well. So the setup would look something like this. You need to have a meter rule which is pivoted at its center. So this is what we are going to do. We are going to have a big meter rule which is 1 meter long, and we're going to pivot it at its center at the 50 centimeter mark. Now you need to hang a bunch of weights from the meter rule, and these two weights could be different, and there could be more than two weights as well. And then you need to measure the distance from the pivot for each of these weights. This, let's call it force F1, and let's call it force F2. Now the way to verify the principle of moments is to adjust these weights. So write down, set up the apparatus as shown, and in order to avoid explaining the diagram too much, just label everything. Label this meter rule, label these your weights, and label this as your pivot, so you don't have to explain everything. So set up the apparatus as shown, and then adjust the weights distances until the rule is balanced. Now once it's balanced, the principle of moments must apply, which is the sum of clockwise moment applied by force F1 should be equal to the sum of anti-clockwise moment applied by F2. Now they must be equal. So the last sentence basically means that you just don't do the experiment once. What you do is you basically use a certain amount of weights, and you set their distances, and you get the rule balanced. You calculate the clockwise and anti-clockwise moments, and you get them to be equal to each other. Then you repeat the experiment with different weights, so then you will have to adjust different distances, and then you perform the whole calculation again, and you still get equal moments on both sides. So you keep repeating this with different values to just verify that no matter what the weights are or what distances are, in the end the moments on both sides must be equal. Alright, now a worker is carrying a ladder, and they have shown the center of mass of the ladder, a bucket hanging from the ladder, and from one point L he is using his arms to keep the ladder in position as well. Now the ladder is wider at one end than the other. Mass of the ladder is 8 kg. Gravitational field strength is 10. Calculate the weight, which is straightforward. Mass times gravity. So remember that mass must be in kg. So if in some question you might get the mass in grams, make sure to convert it to kilograms if you want to find the weight in Newton. So the weight is 80 Newton. Now the thing about center of mass is, when they ask a definition, what is the center of mass? It is the point from where the entire weight of the object seems to act. It's not actually acting from that point, but it behaves as if the entire mass is concentrated, or the entire weight is acting from that point. So it is the point from where the entire weight of the object appears to act. This means that for this ladder, whose weight was 80, the force of the weight of the ladder, which is always downward, is actually acting from this position, from the center of mass. So this 80 Newton force is the weight of the ladder. Now the center of mass is not halfway along its length. It's not right in the middle of the ladder. You can see that there's a lot more length on this side than on the left hand side. So what they're asking is, if the center of mass is not in the center of the ladder, then what does it show? What does it tell you about the ladder? Well, it tells us that its mass is not evenly distributed. If for an object the mass is uniformly or evenly distributed, then its center of mass is right in its geometrical center. So the mass is not uniformly distributed. Moving on, the center of the mass is a distance 90 meter from the shoulder. So shoulder is basically acting as the pivot. Calculate the moment about the worker's shoulder of the weight of the ladder. So this particular force of 80 Newton, which is acting from the center of mass, you have to calculate its moment. Now moment is force into distance, right? The force in this case is 80 Newton, and if you go to the diagram, you can see that the shoulder is the pivot. This right here, the shoulder is the pivot. So the distance of the pivot from the center of mass of the ladder is 0.9, and this is the distance that we have to take. So that would be 80 into 0.9, and that must give us a value of 72 Newton meter, because the force was in Newton and the distance was in meter, so your moment is in Newton meter. Now the weight of the bucket is 87. Let's label it on the diagram without wasting any time. So weight of the bucket, which is hanging from here, is 87 Newton. And then there is and the distance of the bucket from the pivot is 1.3. Now the worker keeps the ladder horizontal by exerting a vertical force at point L. So the bucket's weight and the ladder's weight do not produce equal moments. Therefore, the ladder on its own would not balance on the person's shoulder. In fact, he has to exert another force from this point using his hands, a vertical force, which will keep the ladder balanced. Now, what we have to do is find this force. Not only do we have to determine the size of this force, we also have to determine the direction of this force. So, the thing about this question is you do not know whether the force is acting upwards or whether it's acting downwards. What I'm going to do is I'm simply going to assume that the force is acting upwards. I'm just going to call this force F. All right, and its distance from the pivot is 0.4. I don't know whether the force is upwards or downward, but I'm just assuming that he's exerting an upward force. And even if my assumption is wrong, I can simply write down the correct answer and you will see why. So what we are going to do now is we are going to do the entire calculation by using the principle of moment. Since we know that the ladder is balanced, we can apply the principle of moments to this ladder. So how would you do that? First, let's take up all the clockwise moments. The principle of moments is pretty straightforward. Sum of clockwise moments must be equal to sum of anti-clockwise moments. Now the clockwise moments that we are dealing with is because of the weight, the 80 Newton force, which is 80 times 0.90. Now remember, we have already found this was coming out to be 72. Is there any other clockwise moment acting on the ladder? No, it's not. So we are done with all the clockwise moments. Put the equal to sign and go to the right hand side of the equation. Now let's take a look at the anti-clockwise moments. The bucket's weight is exerting an anti-clockwise moment, so that would be 87 times 1.3 from the shoulder. And there is another force F that is acting upwards according to our assumption, and that needs to be also added to the anti-clockwise moment. So that would be F times 0.54. Now when you make this equation, what you will do is you will find the force F. So let's find the force F using this equation. I'll put it all in my calculator and I'll find out the force F. And force F is turning out to be minus 76.11 Newton. Now you know that the force is not a negative quantity, but the negative sign here represents something very important. I simply assumed that the force was acting upwards, but my calculations told me that no, the force wasn't actually acting upwards. The force was actually downwards, and that is why there's a negative sign with my answer. So all I need to do when I write down the answer is just ignore the negative sign. Let's just ignore the negative sign and write down my answer, 76.1 Newton. And when I state the direction of the force, I assumed upwards. I assumed the force is upwards, but the negative sign means that the force is actually downwards. So I'm just simply going to write my answer as downwards when mentioning its direction. I hope that's clear. Now we'll move on to the last question of this paper, question number 9, and this is mostly dealing with electricity and the related topics. So we have a lamp which is connected to a 240 volt AC supply. Describe how the output of an AC supply differs from an output of a DC supply. You can sketch two voltage time graphs to help your explanation. In fact, helping our drawing the graphs here is much easier than just describing what is going on. So we'll draw this graph for DC. This is on the y-axis we will have voltage, and on the x-axis we will have time. So time versus voltage. The graph for DC is just a simple straight line. Either it can be in the positive or it can be in the negative. So basically DC, or direct current, flows in one direction. One direction and is steady. The steady part doesn't have to be necessarily there, but the main point is that the direct current flows in one direction. On the other hand, the alternating current has both positive and negative values, and this is what the graph of alternating current looks like. So the positive and the negative values means that the direction is changing, and also the magnitude keeps varying. So what will we say about AC? AC changes direction and magnitude repeatedly. Alright, now a lamp is rated at 60 watts. Now when you say rated, this word is very important, and it doesn't get taught in classes like it should be. But when you're doing past paper and you hear the word rated, and then you see a value of power or current written next to it, that basically means that if the lamp is working normally, lamp is working normally, then it must give an output power of 60 watts when it is supplied, when it is used with a 240 volt supply. So they're saying, okay, you now know that when the lamp is working normally, it gives an output power of 60 watts and connected to a 240 volt supply, then what would be the current in the lamp? So for that, all you have to do is just use the equation for power, which is current times voltage, and power is 60, current you have to find, and voltage is 240, and therefore the value of the current would be, let's calculate this, that would be 0.25 amperes. Alright, pretty easy. Now you have to calculate the resistance of the lamp, and now there are multiple ways of doing it. For resistance, you can use the defining equations, which is potential difference upon current, V over I. You can also use the equation of power, which is V square over R. You know the resistance, you know the power, and you know the voltage, so you can find the resistance. In the first equation, you know V and I, so you can find R. And also you can use this equation, I square times R. You know I and you know P, so you can find R. I'm just gonna use V over I, so that's gonna be 240 over 0.25, and the answer would be 960 ohms. Moving on, the room is lit by 5 of these lamps connected in parallel. Two advantages of connected in parallel rather than in series. Okay, let's take a look at some lamps connected in parallel. If the lamps are connected in parallel, they would be connected somewhat like this. All of these lamps are going to get 240 volts. But if they were all connected in series with the power supply, then they will have to share the 240 volts of the power supply, and if they are all identical, they will share them equally. So 240 over 5 is around 48. That means each of these is going to get 48 volts across them. Each of them will get 48, right? But in parallel, all of them are going to get 240 volts altogether. So in the parallel circuit, you know that the resistance of the overall circuit, the parallel combination, would be much less. In fact, the resistance of these 5 lamps in parallel would be 960 over 5. 960 over 5 that means that the overall resistance of these 5 lamps in parallel would be 192 ohms. On the other hand, if you were to connect all of them in series, their overall resistance would be actually 960 times 5, which is 4800 ohms. So obviously, if the resistance is much larger, then the current flowing would be much small, whereas the current flowing from here would be much larger. So each lamp gets the required amount of current that they need. They all get the required amount of current that they need, right? And they will be working at normal brightness. Now point number 2 would be, which is pretty basic, that if any of these lamps were to go out, let's say this lamp goes out, it blows, its filament breaks, then the current can still flow through all the other branches, so they will keep working. But if, let's suppose, this lamp's filaments breaks in the series circuit, now there is no path for the current to flow, so all the lamps will stop working. If one lamp breaks, all will stop working in series, but this is not going to happen in parallel, so you can write that down. Moving on, now you have 5 lamps. That's 5 lamps are lit for an average time of 5.5 hours each day for a year. The cost of electricity is $0.15 per kilowatt hours. You have to calculate the total cost for using these lamps for a year. So obviously cost is calculated by energy consumption, which is obviously which has to be in kilowatt hours, times the rate which is 0.15. But in order to calculate the energy, what you do is you do power in kilowatt multiplied by time, which has to be in hours. If you want the energy to be in joules, then it's the same equation, power into time, but then the power would be in watts and the time would be in seconds. Right now we want the energy to be calculated in kilowatt hours, so make sure that your power is in kilowatts and the time is in hours. Now the time would be pretty straightforward. You have 1 year, so how many days are there in 1 year? 365 days, and for each day they are lighting the lamp up for 5.5 hours. So this is the total amount of hours that the lamps are used for. The power in this case can be found from the previous part. In part B, it was stated that the rated power for each lamp is 60 watts. Now we have a total of 5 lamps, so 5 into 60, that is the total power for the lamps, but that is in watts. So in order to get it into kilowatts, this has to be in kilowatts. You have to be divided by 1000. Now this will give me the energy in kilowatt hours. So let's first calculate the energy. Now when I calculate the energy, I will get 120.45 kilowatt hours. Now this is definitely not the answer. Once you have the energy, you can now put this here and then multiply it by the given rate. So the energy is 120.45 and the rate that was given was 0.15. So once we calculate this rate, we get the answer 18.1. So we can write that as dollars 18.1. This is the total cost of running 5 lamps for 5.5 hours a day for a year. Student takes the lamp in B, so they are the same lamp, and connects it in a circuit using 1.5 volt cell, an ammeter and a voltmeter, and he wants to determine the resistance. You have to draw the circuit diagram to determine the resistance of the lamp. Alright, so whatever is told to you, just mention all of that. So this is a 1.5 volt cell. You should definitely have a switch, and then you need to have an ammeter in series with the lamp, and what you need to have is a voltmeter connected in parallel to the lamp. These are all the things that you need to determine the resistance. Now the value of the resistance differs greatly from the value calculated in B. State how the resistance value differs and why it differs. Now you must remember that the IV characteristic graph of a lamp, current versus voltage graph for a lamp, kind of looks like this. And you should know that the gradient of this graph is decreasing. Now remember, in any of these IV graphs, the resistance is inversely proportional to the gradient. So when you see this graph, you can see that the gradient is decreasing. Therefore, the resistance of the lamp must be increasing for higher values of voltages and currents. For higher values of resistances and currents, the resistance, for the higher values of currents and voltages, the resistance is high. But for lower values, you can see that the gradient is steeper. Therefore, the resistance must be low. So obviously, initially our lamp was connected to 240 volt supplies, and now it's been connected to a 1.5 volt cell. So that's a much lower value of voltage and therefore current. So the resistance would be lower. So what we can say, resistance of the lamp would be lower. Now we have written down our answer, but we have to also explain why it differs. Well, this actually has to do with the temperature of the filament. The hotter the filament, the more its particles vibrate, and therefore the harder it is for the free electrons to pass through the lamp. Now, for a colder temperature, the atoms are vibrating much less, so therefore it's much easier for the electrons to flow through the filament, and therefore the resistance is lower. So the reason would be temperature, lower temperature. So this is it. This is the end of the paper. Hopefully you understood all the questions, and I'll try my best to post as many as I can before your exams arrive. So look out for those. I'll see you in the next one.